All right, the purpose of this video is to sort of investigate when it is appropriate to use a normal model to approximate a binomial model. So what I have here is an Excel spreadsheet where n is equal to different things. We have 4, we have 10, we have 30, and we have 100. Okay, and I'm able to input what p is. So remember, a binomial model has n and p. And so I'm going to input 0.5. And so we can see that this histogram represents the binomial model when n is 4 and p is 0.5. We can see that, yes, it looks symmetrical, but we certainly know that it's discrete. And if I were to use a normal model to approximate it, there would be lots of error in that model because we're not able to account for certain things. I can see with 10 trials, it's still discrete, but there's more outcomes, and so it looks like a better approximation, but certainly it's not going to be very good. If I go to 30 trials, it looks better, but there's still going to be error because this is still discrete. And if I go to 100 trials, well, that certainly looks like a smooth normal curve, but we still know there's some error, but the question is how much is the error? Okay, and we actually found out in the problem previous that when n is 100 and p is 0.5, a normal approximation works pretty well. And you can sort of see that in this diagram or this histogram of the binomial model. Okay, now what if I change p? What if I change it to like something really small? Let's say 0.05. Okay, now you can see that for 4 trials, the distribution is very, very skewed right. A normal model would never be appropriate for that. For 10 trials, certainly never would be appropriate. 30 trials, never appropriate. 100 trials, well, we know it's way skewed right, but, it's not that bad. I could overlay a normal model and not be off by that much, but it still doesn't seem like a very good approximation. Okay, so now what if I change that probability to 0.1? Okay, we can see 4 trials skewed, 10 trials skewed, and we also know that these are so discrete that it doesn't seem to work. And this is definitely still skewed, but not as skewed, and then this actually looks not that bad. So it's almost like a normal model might be somewhat appropriate when p is 0.1 and n is 100. Okay, so here's what I'm going to do. There's a little macro here that will gradually change p when I do this little thing. So I'm going to press this button, Control S, and actually you can sort of see it's like the wave is occurring here. All right. So it looks kind of cool, and once you get over the coolness, I want you to kind of think about what you're seeing here. All right, now hopefully I can get it to stick on. I'm actually going to move these up so that I don't have to worry about it. I'll pause it for a second. All right, so I'm going to do it again, and I just want you to look at the 30 and the 100 here. Okay, so I want you to say, at what point does this look normal, or at what point does it look non-normal? I mean, look at the 100 trial one. That kind of looks normal now. P is like 0.6, still looks normal, so forth. Okay, now at what point does it start not looking normal? Okay, so I'm going to do it again, but I'm going to pause it here. Okay, now notice that P is very low, and we can see that when n is equal to 30 over here, we know it's still very discrete, so we know that's a problem. But it also looks sort of skewed, but not that bad. When n is equal to 30, or n equals 100 and p is equal to 0.06, we can see here that this, still looks kind of skewed. It doesn't look that normal, but I'll continue here. Okay, so now we're up to like 0.2. Let me pause it. Okay, now how do they look? Okay, 30. I don't know, that we know that the actual model is discrete, and so a continuous model like a normal model won't be perfect, but it doesn't look that bad here. And certainly for n equals 100, it doesn't look that bad. Okay, so let's continue. All right, we're moving on. All right, we're awfully close. Okay, now we're in 0.6, 0.7, 0.8. pause it. Okay, we're at 0.97. All right. Now the 30 certainly doesn't look normal. It's way skewed left. The 100 also doesn't look that normal. Okay. And we finish it off. And then we get back to 0.5. Now, I want you to ask yourself, when do these look the most normal? All right, sort of talk to your neighbor for a second. Well, isn't it right now when p is 0.5? Because when p is 0.5, at least for this, or for these, the binomial model is symmetrical, exactly symmetrical. The normal model is symmetrical, and so that's close. Now, the 100 is better than the 30 because this has got less outcomes than this. So if we're approximating a normal curve with this for a binomial model, we're going to have more error here than we are here. Okay? So it's kind of like, well, when is a normal model appropriate? Well, the closer to 0.5 that we are, the better it's going to be. And also the bigger n is, the better it's going to be. Okay? So there's a rule of thumb, and I'm going to pause it and then I'm going to write it down for you, for when a normal model is a pretty good approximation for a binomial model. All right, so here's that rule of thumb. A normal model is a good approximation for a binomial model when n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. This is the expected number of successes when that is bigger than 10, and this is the expected number of failures. Notice this is not the formula for the variance or the standard deviations. It's n times 1 minus p. It's not np times 1 minus p. This is the expected number of failures. When those are bigger than or equal to 10, then a normal model works pretty well. Okay, now the question is, if we could use a binomial model, why would we ever use a normal model? We really haven't addressed that. It's like, well, why would we ever do this? We know the binomial model is exactly correct. Why would we use, first of all, a continuous model for something that's discrete, and so forth? Well, the answer lies in when we have to combine binomial random variables, when we have to take the sum of binomial random variables, or the difference of binomial random variables. There are many contexts where we do that. A normal model is going to be so much easier, and it's still going to be a really good approximation under these conditions. Okay, so we're going to investigate some problems where using a normal model or a normal approximation of the binomial is really, really useful. Okay, but here's what I want you to get from this. Okay, and we can sort of see that here, is that when n was small, okay, you know, here p is 0.5, n times p here for n equals 4 is 2. Well, that's not going to be a good approximation at all. A normal model is not going to approximate this well. Even when n is 10, a normal model pretty much never, and this is not working, I can't see, oh, there it is. No, right here. A normal model really is never going to be good because it's really just too discrete. The binomial model is too discrete. But if we're at n equals 30, n times p is 15. n times 1 minus p is 15 as well. It works pretty well. Okay. What if I change it to, how about 0.4 or something like that? Well, n, and I'll do that. This thing here. So what if I change it to 0.4? Well, you know, this one looks still pretty good. This one looks still pretty good. What if I change it to 0.1? Okay, now this one's no good, but n times p is 3 here. So this is too skewed. It doesn't work. Well, even here, this is sort of the cutoff for when it works well. For, I can't see it. Here's the 100. This is sort of the cutoff. Okay, and I can see that a normal model still would work pretty well, but this is really the lowest p could be. And similarly, if I change it to 0.9, it's going to be all over on the other side. That's sort of the best case scenario here. Or actually, the highest p could be where a normal model would still work here. If I change it to 0.95, now a normal model is no longer appropriate. Okay?